Thank you everyone for joining this evening's IAAC lecture series with Nadya Peek. The lecture this evening will be called Machine Agency, Rapid Prototyping of Creative Automation. I'd like to welcome you, Nadya, and thank you so much for joining us. By the way, my name is Matilde Marengo, I'm Head of Studies at IAAC, and I'm going to introduce quickly Nadya. So Nadya Peek develops unconventional digital fabrication tools, small-scale automation, networked controls, and advanced manufacturing systems. Spanning electronics, firmware, software, and mechanics, her research focuses on harnessing the precision of machines for the creativity of individuals. Nadya directs the Machine Agency at the University of Washington, where she's an assistant professor in human-centered design and engineering. The machines and systems Nadya has built have been shared widely, including at the White House Office of Science, Technology and Technology Policy, the World Economic Forum, TED, and many maker fairs and outreach events. Her research has been supported by the National Science Foundation, the Alfred P. Sloan Foundation, and the Gordon and Betty Moore Foundation, and her teaching has been recognized with the University of Washington's Distinguished Teaching Award for Innovation with Technology. She received the MIT Technology Review's 35 Under 35 Award in 2020. Nadya is an active member of the global Fab Lab community, as well as being on the board of Open Source Hardware Association, and half of the design studio, James and the Giant Peak. She plays drum machines and synths in a band construction and got her PhD at the MIT Center for Bits and Atoms. So thank you so much for joining us, Nadya, this evening. And we look forward to hearing all about the Machine Agency.
Yeah, awesome. Thank you, Matilda. Yeah, once my band performed at IAAC during Sonar, I think it was 2018 or something. But this is a very different lecture, so it's nice to, I guess, sort of meet all of you. Please stop me if you suddenly can't hear me or something like that. And I'm going to talk about my research in my group, Machine Agency, where broadly the goal is understanding how we can harness the precision of machines and automation, but for the creativity of individuals, for things that you might just want to improvise with or do as one-offs. I think when people think about digital fabrication, it's easy to kind of go back in time and think about the history of where did these things come from. And a good place to start is maybe where we first got computation. So here is the first, or one of the first general purpose computers, the ENIAC machine, which was developed during the Cold War, or at the start of the Cold War, the end of the Second World War, as part of wartime efforts to be able to do calculations for artillery firing tables. And because of the military push, there was a lot of money to invest in new technology like general purpose computing. But once those investments were made, they were quickly repurposed for other kinds of applications. So less than 30 years later, the technologies that were developed with these military applications were suddenly being recast into these different situations, like personal computing. So suddenly it wasn't just about these types of calculations, but it was also calculations for wartime efforts, but it was about word processing and education and what are ways in which computation could help individuals do different kinds of things. And fabrication was also a big topic at the time. This is maybe from 1952 from Popular Mechanics. So the same time that the first digital computers were being developed, people were trying to connect them to CNC mills and other kinds of fabrication machines. This is a setup that was at MIT at the time, where they were trying to figure out how to use calculations to determine the position of the mill so that you could start milling complex curvature like the things that you might need for airplane wings or other parts of flying vehicles. And I think a lot of people thought that this would go in the same way as the personal computer. We would go from general purpose industrial computation to personal computation, and therefore we would also go from general purpose fabrication that was in an industrial context to a personal fabrication. And that's definitely what a lot of my my advisor, Neil Gershenfeld, and many other of his colleagues really thought of this as the future. Personal fabrication is going to be the same story arc of going from industrial computation to personal computation. It's going to be the same story arc from industrial fabrication to personal fabrication. And it's going to basically be like what was promised to us in science fiction. We're going to walk up to things in our home, like replicators, and we're going to be able to tell them exactly what we want, and they're going to understand everything that we need and just give us the parts or the food or whatever it is that we have. But as someone who works a lot with fabrication, this is like not exactly the reality that we inhabit. This is a milling machine that is at NASA Ames, where I collaborate sometimes with my colleague Kenny Chung. And if you look at this milling machine, it's a computer-controlled milling machine that you can use to make large metal parts. Mills a lot of fancy titanium parts that end up going into space. And yeah, it maybe seems like a cool high-tech piece of equipment, but actually this milling machine is the same model as the milling machine that you see in this picture for popular mechanics. The only difference between this milling machine and this milling machine is that one of them runs Windows 7 and the other one ran on punch cards. And so, you know, I guess like there's a lot of ways in which maybe modern computation has made it easier to use machines like this, but there's not really something totally different in how we interact with these machines, or how we tell it what we want to build and how we're building it. Now, at first I thought that maybe this is just an education thing. It takes a while to learn how to use a milling machine. And so how do you make it easier to learn how to use a milling machine? Maybe if you all had lots of smaller milling machines, it would be much easier to be able to, learn how to do the programming and play around with making different kinds of things, and yeah, ultimately be really comfortable using digital fabrication. So here are milling machines that I worked on as a graduate student at the MIT Center for Bits and Atoms with Jonathan Ward and others. David Lakatosh here in the picture. And the idea was that you could go up to a milling machine, like a CNC mill you might have in your fab lab, and make a smaller milling machine, and then take that home and use it whenever you want. So this was an open source machine that was made out of cutting boards that snapped together, and you could use for milling circuit boards or wax blocks or other things that maybe you guys are familiar with doing at IAAC. And there really the idea was, well, if we can sort of make it, if we can make the access exponentially grow, because anyone who uses a milling machine can now make a milling machine and therefore have a milling machine, then it will become much easier for people to learn more about milling, and they will do it much, much more. That wasn't really the case. There was not actually there were not a huge number of people who built this machine despite it being open source. So we thought maybe the reason is like the functionality of this milling machine is the same as the functionality of milling machines that you can buy off the shelf. And so maybe people want something much more different or unusual. And so with Alon Moyer, I worked on something that we thought was going to be more like the laptop of digital fabrication. This is PopFab, which is a multi-type fabrication machine that fits in a briefcase, and you can open up and you can put different heads on it. So here is a 3D printing head. It also had a milling head and a sticker cutting head. I don't know, it had all these things that it could do in this one pop-up work envelope. I don't know, it was sort of fun to carry this machine around because it did give you portable access to digital fabrication as opposed to having to go to the Fab Lab or to a place where the machines were much bigger. But then there were other problems with the size. Ultimately, like, you couldn't make anything bigger than this work envelope. You couldn't, it was just like having access to a small tool that you carry around. And that was a major difference with a laptop and a supercomputer. Like, if you calculate something on a supercomputer, you get a number out, and you calculate the same thing on a laptop, you get the same number out. It might take much longer, but you don't get a different result. Whereas the difference between what you can do on PopFab versus what you could do on a large format milling machine like this was just totally different. And so personal fabrication was just sort of this small facsimile of what was being done at an industrial scale. And so despite having lots of fun building small machines that did similar things to bigger machines, I kind of came to the conclusion that it wasn't so much the learning how to use digital fabrication machines that was the problem, but more so that they weren't actually doing any of the things that people wanted to use them for. And even if they were very precise, you couldn't use them in lots of different contexts. This machine, despite it being portable and being able to bring it to lots of different places, couldn't work in its environment. It couldn't, you couldn't change the context it was in. You could only make things within this tiny work envelope. And so thinking about, what does it mean to have precision as a creative tool, and how do you use it in these different contexts? And working with a lot of people who are talented machine builders, starting to wonder, like, where does this really need to go to make precision really into something that you can employ creatively in different contexts? And Alon, who was working with on PopFab, he at some point needed a lot of coils because he was making electromagnets, and he made this little machine that I really liked. It's just 2 motors with a laser cut body, and the only thing it does is make these coils so that he could control the pickup and drop off of warp threads in a loom that he was making. And it wasn't like he needed a ton of these coils. It didn't have to be super fast. He didn't need really high efficiency in the production. But what he needed was all of the coils to be exactly the same. And winding them by hand would have been really tedious and a lot less precise than this machine that he was able to really rapidly prototype using digital fabrication tools. And so it made me start thinking about, okay, what goes into the rapid prototyping machines, and how do you even define what the machine is and what it does? This is an example that I think is really telling about how to be able to reconfigure a machine to do something that you want. These are architecture students who are doing like a complex surface. They're cutting a complex surface out of styrofoam, which you see on the right. And they made their own CAM module in Grasshopper. They're doing all these complicated calculations. They have this cool robot arm that they can control using Kuka PRC. And then they're cutting the styrofoam with this hot end. So the knife is at the tip of the robot arm. And the temperature control of that knife needs to be such that it cuts the styrofoam well, but doesn't melt it too much. And to be able to control that temperature, they're trying to get this done. It's late at night. They just asked the guy who's standing here on the left to flip the switch on the surge protector, turn it off if it gets too hot, and turn it on if it gets too cold. So despite us having access to all of this technology, and there's all this computation, there's so many people involved in this project, the system integration to this machine was so complicated that the fastest way to do this and the cheapest way to do this was just to have someone stand there the entire time during runtime, controlling something that would have otherwise been an extremely simple control algorithm to write. And so there's something really silly about that, you know, using machines, hacking machines, making machines, like the threshold somehow is really in a place that is optimized for people who are going to use these robot arms to, you know, pick up a bag of cat food and put it onto a pallet as fast as possible, as many times a day. And not for these types of contexts in which people are trying to experiment with the precision, trying to figure out what the possibilities are of digital control and what the interplay between the digital design and the physically manufactured parts are. And so that's really where I decided the crux of it lies. It's not using the machines, but it's understanding how to hack the machines to do different workflows. And if you can't hack machines to do what you need, then to be making entirely new machines to make that possible. So not so much optimizing during runtime, but more figuring out how to lower the threshold to set up. So I started experimenting with what that would mean. Like, how do you make it as easy as possible to set up lots of different digital workflows, digitally controlled workflows. So together with James Coleman, I started building all of these little modular machine parts. So these are linear stages and rotary stages and different machine modules that you could connect together in different ways, so that you could build machines sort of on the fly. And an important part of this was not just the stages, so here we are doing more foam cutting, but also the controllers that allowed you to just add more and more components to the machine as you were doing different things. So here I'm plugging in these little Gestalt nodes, which we worked on together with Alon Moyer again, to be able to control each module individually, but as a network of components that you could then all talk to at the same time. And so as you were adding different functionality or different parts to the machines, you didn't have to redesign the whole control board, or you didn't have to rewrite the firmware. It was a matter of adding and removing things from the network. Yes, very serious fabrication task. And so that way you're also able to interface with different kinds of design software to be able to build your toolpaths in lots of different experimental ways. Here's like a part that I think I would be very, very hard pressed to make by hand. Styrofoam thing that says hell on one side and yeah on the other. So it's just like the kinds of things that you can do if you have control that are so difficult or almost impossible to do by hand. And that if you want to change anything about the machine, instead of adding a person flipping off and on a surge protector, that you're just adding another node to the control network. And when you add another node to the control network, you describe that node in what we call the virtual machine in a Python library that we wrote. Yes, and the Python library basically allowed you to also switch out virtual machines that were maybe talking to different software applications or different physical machines as sort of a lightweight interface layer. So say you wanted to talk from your own Python script, you could then talk to the virtual machine object, which would then control the machine. Or if you wanted to change the machine, say you were using a small machine and now you wanted to change to a larger machine, or you wanted to change to a machine that had a different drivetrain, you wouldn't have to change anything about the design, the toolpath design software. You wouldn't have to change anything. And you would only have to change the virtual machine object to make sure that you're describing the correct machine. So you can control it from Grasshopper, or you could control it from mods. I don't know if you had IAAC in the Fab Lab are using mods, but you know, ways of controlling machines from browsers or creating different interfaces, and really making it easy to set up lots and lots of different kinds of workflows. Here is a machine that we built very quickly for then Janet, who needed to have this airfoil at very short notice. And so we set up a machine to cut a much bigger version of the example cuts that we were making. We made different 3D scanning machines and image capture machines. And we made a lot of different machines with these modules. But problem was that just we had the modules. They were like the MTM Snap that I showed you before, and like PopFab, all of these things were open source, but nobody else was building them. And part of it was maybe just that it was too hard to build a lot of the machines that we designed. Like PopFab was water jet cut and required a lot of complicated assembly steps. The MTM Snap was maybe slightly easier to make, but still required some complicated system integration. There's just like not a lot of people building the modular machines components that we had built. They were all made out of sheet metal and things that you needed maybe a brake for, or other sheet metal working tools. And it was just not something that other people were taking on. So James, Alon, and I decided to make a much more lo-fi version of the modules out of cardboard. So we developed a cardboard machine kit with the idea that you could really quickly prototype a machine, and the point wasn't to replace existing machines. So we're not saying like, oh, get rid of the Cincinnati Hydrotel at NASA Ames and replace it with a cardboard machine. No, it was, if you don't have a machine and you want to experiment with how to quickly build one, kind of in the spirit of Alon's coil winding machine, then how do you make that as easy as possible? So the cardboard machine kit was laser cut cardboard. So you use the precision of the laser cutter to be able to make the frame. So here I am laser cutting, and you're partially scoring and partially cutting through the cardboard to be able to do accurate folding. Here are the Gestalt nodes for the network controls, and the cardboard stages had different positions in which you could connect them to each other. So the idea was that it wasn't supposed to be months before you had built a machine, but a matter of hours, or that you could really prototype computer-controlled motion very, very quickly. And we actually used this in teaching in Fab Academy for a few years, where lots of people in Fab Labs all over, including at IAAC, made a bunch of different kinds of machines with it. So machines for plotting and machines for coffee mixing. This is like an iPhone 3D scanner. And a lot of these machines, like, they're not like the most fancy or serious things. They're doing like funny stuff like light shows and cocktails and ketchup. But it was the possibility of iterating with, nobody was thinking, oh no, like here's a scary machine and I don't know how to hack it. Everyone is like, oh yeah, it's just like a bunch of stuff that I put together made out of cardboard, and I can like easily add an extruder, or I can easily add a syringe, or I understand how to interface with and modify that. And that kind of iteration allows for using things in lots and lots of different ways. Yeah, maybe I can show you this specific, this is like a specific example of one of my favorite machines from Japan, from the Fab Lab Sendai. It's for daikon radishes. And you can see that they have like some digital fabrication skills already. They're like good at 3D printing, and they have these motors, and they have these modular controllers that they're connecting to each other. And even in this 2-week Fab Academy assignment, you can see them learning different things or doing different things to be able to understand how to automate this peeling of a daikon radish that they want, or making daikon radish noodles. So they added this tailstock. They like looked at different things that had to do with the starting speed and the amount of force that was necessary to start versus to continue. Yeah, and you know, these daikon noodles, it seems kind of silly, but it also seems like the kind of thing that would be mega tedious to make by hand. So just the idea of making inexpensive, quick turnaround little kitchen robots. I love it. I think it's very funny. There's another machine from a fab lab in Mexico where they wanted to have also a super application specific machine for connecting PVC tubes together at different angles. So to be able to connect them together at different angles, you have to cut them in different, you have to be able to cut curves into them. You can't just cut them straight. And so this is a hyper specific machine just for cutting tubes of this size and different curved tool paths. And because it's just a very small structural loop, because you're only using this tiny drill bit, just tiny end mill, you don't actually need to make the whole machine out of, like cast iron or the traditional kind of machine building materials. But experimenting with, okay, I need this particular cut, and I'm going to put together this machine to make this as easy as possible. Yeah, I don't know. I thought these are two great examples. Exciting stuff. So with digital fabrication, I feel like it's not, people often think of, oh, digital fabrication is just like one machine. I'm going to go up to the 3D printer and that's the machine that I'm going to be using. But actually, I think digital fabrication is the creating of all of these different workflows that span materials, computation, design. Like there's all these different parts that can be varied, that are interdependent in different ways. And it used to be that those things were all actually separate jobs. Like there was someone who did CAD, and there was someone who ran machines, and there was someone who programmed. And those people had to communicate with each other. And all of these things ended up sort of developing in these siloed environments. And so sometimes the most difficult thing about doing digital fabrication or different kinds of computer controlled workflows is how to translate from one to the other. I'm sure that you at IAAC have had lots of trouble where you wanted to export something in some format, and instead you needed to export it in DXF R11, or there's all these problems in translation that happen that are difficult. And like, how do you support that? How do you support the making of the workflow and being able to test in lots of different times or different insertion points? How do we make tools actually for creative automation? And when I was in school, what we were taught was you start from design intent, and then you make a digital model, and then you slice it, or you make the CAM for it, you create the machine instructions, and then the machine makes the final product. And then you iterate, and that's how digital fabrication works, this sort of canonical workflow for digital fabrication. But when you look at what people are actually doing with digital fabrication machines, and over the pandemic, my group, my student Hannah Twigg-Smith, has spent a lot of time looking at plotter Twitter, the hashtag for sharing different kinds of plotted art. Really what we found is it's not this canonical workflow at all. It's people constantly experimenting with different pens and papers, and like experimenting with different speeds. They're not all trying to have this seamless user experience. They're really trying to iterate and develop custom workflows that allow for lots and lots of different kinds of exploration. And so when we develop tools for that, how do we support that generative and iterative kind of work? Rather than seamless experiences, how do we support creative practice? And so that, I think, has to tie further down, not just modularity in the machines, but also modularity in how we talk to them and how we extend them. And so for machine design and machine building, kind of has changed my approach. Rather than making things that look really slick or fancy, how do we make things that are actually easy for other people to build? How do you make it fabricatable, that you have limited equipment required to be able to build the parts, and that the putting together of the design isn't super complicated. Whereas with the MTM Snap, you needed like maybe several people to hold parts at a certain time to be able to put it together. How do you make that super easy, the assemblability of the design super easy, as well as the documentation, something that that a lot of people can follow without necessarily having the same expertise that you had going into the project. And how do you also include maybe in the design all the tools that you need for building the design? Here we're pressing these pins into this 3D printed part, the blue 3D printed part, and then underneath there is just an orange support part that's holding the 3D printed part, such that the pin is going in exactly at 120 degrees or 90 degrees with respect to the table. And so, you know, it's a very different kind of design criteria, or very different design goals than you would otherwise see in industrial machines or machines that are made for really high efficiency and high throughput. Instead, it's more about extensibility and being able to be customizable by other people. And how do you also support them? So we in my group, we have we support a lot of active Discord communities for people who are trying to build our machines. Instead of just saying, you know, like, read the manual, how do you actually really support and understand who is trying to build and extend them? So one such machine is Jubilee. Jubilee is, yeah, kind of similar to PopFab, but in that you can change tools to have different tools on it, but it does the tool changing automatically. So you can pick up and drop off different heads to be able to use different tools in one workflow. So for example, so it has a cable-driven tool lock. So here it is picking up, or here is how you would attach, for example, microscope tool head. Has a little wedge plate, and then there's a twist lock that holds it in place. And this is a kinematic mount, just like in PopFab. So whenever you pick up and drop off the tool, it ends up in exactly the same place. The bed plate is also a kinematic mount, so you also don't have to re-zero every time you remove or put back the bed plate. Yeah, you can do a bunch of different kinds of operations. You can pick up and drop off pen tools, or a lot of people who use Jubilee use it for multi-material 3D printing. So you can drop off one extruder head that's printing in blue and pick up another extruder head that's printing in orange, or using Jubilee for with its syringe head for doing different kinds of liquid transfer, to be able to do different kinds of yeah, I don't know, bio stuff. Increasingly, we do a lot more with science experiments, workflows, not just different kinds of fabrication steps. Yeah, and I guess unlike maybe some of the other machines we made that were sort of more slick in terms of their industrial design, Jubilee is really designed for A, automatic tool changing, and B, being able to do these really heterogeneous workflows. For example, to be able to do microscope inspection of something and 3D printing in an automated fashion. So you can drop off a microscope and then pick up a different kind of tool to do something totally different. And instead of just for fabrication, people are increasingly using this for doing things like how do you create automated diagnostic tests? So if you can gather images, and then if you can gather images of a sample and then do something with them, how can you use computer vision and other tools to automate some of these parts? We're also making kind of novel manipulators for picking and dropping off things. So if you don't want to touch a sample, for example, this is an ultrasonic manipulator that can pick up small things and keep them in what we call a virtual container. So you can then suspend, this is like a styrofoam pellet, but you could also suspend water or small insects in air. and then drop them off without ever having to interface or without ever having to touch them, maybe damaging them. I've been talking at you for a while, so I'm going to speed through maybe a few more things, and then I'll let you ask me questions because I, don't see anyone, so it's sometimes hard. This is a project by one of my PhD students, by Hannah again, who's creating different kinds of browser-based controls for controlling machines, not just one machine at a time, but if you're using several machines together, one for sample preparation and one for sample manipulation, how do you control the overarching workflow between them? This is Jubilee that Joshua and Hannah customized to be able to sonicate samples to do different kinds of chemical engineering experiments. Or here is another machine that we use to do sort of automatic robotic transfer of these tiny plants called duckweed. So we can do this kind of progressive imaging of duckweed, and also picking up and dropping off duckweed in different well plates and being able to do different things with it. So really a lot of like experimenting with developing different kinds of workflows for doing strange things that maybe, there isn't really a market for. So there's not going to be a company that's going to sell duckweed handling robots, but there still might be a project in which you want to robotically handle duckweed. Unceremonious drop off. Yeah, and also, what are the effects of the machine, coming back to fabrication, what are the effects of the different kinds of machines and toolpaths on the material itself? So this is a Grasshopper Library that Frick, another machine agent, has been working on in Norway to be able to interactively control not just the geometry of the toolpath, but things like the acceleration and the jerk, to be able to really control different elements of, what the material will actually look like afterwards, based on how fast and how you might move the machine around. Yeah, I'll tell you more about that if you ask about it in the questions. Blair, another machine agent, has been developing ways in which you can control digital fabrication machines directly from the creative coding environment p5.js. And so instead of 3D printing, for example, with a slicer, being able to make these sort of experimental and weird 3D prints where you're doing things like bridging or printing with blobs or printing kind of foam or sponge-like structures. We also work with Eleftheria Rumeli's lab. She does a lot of work, here she is, she does a lot of work developing fully biodegradable plastics or plastic-like materials out of, so unlike a PLA, which needs special conditions to biodegrade, her materials just biodegrade on their own. Here is some of her biomaterial-based filament, and she develops a lot of different materials. She's a material scientist who develops a lot of different materials out of things like spirulina or kelp or matcha. And we've been experimenting with, well, what are the material properties of this, not just in tensile tests and in other kind of standard material science evaluation, but what are like the objects that we can make with it, and how do we, what are the objects that we can make with it, and how does that differ from the kind of fabrication that we've been used to and doing before? Anyway, so this may be a big whirlwind tour. I just want you to think about, like, what's the difference between the Cincinnati Hydrotel and what you can do with a machine like this, and all of the things that you might build, different materials or different experiments or different ways of hacking and making machines. Machine Agency is my research group at the University of Washington. There's lots and lots of people in it. You could come visit if you ever come to Seattle. And yeah, thank you for your attention. And let me know if you have any questions.
Thanks so much, Nadia, for the lecture. I don't know if you want to stop sharing the screen so that we can see people.
Yeah.
Fantastic and super, super, super interesting. Just for everyone who's following, as I wrote in the chat before, feel free to write your questions in the chat or to raise your virtual hand and you can unmute and ask the question directly. To start us off with, Nadia, I was really interested in two specific things. One was something that we have a parallel sort of situation in the construction industry, definitely, which is the question of how things are developed in some way in silo environments. No? So there's the question always of how do you communicate the data or information from one part to the other. And it seems like you guys work on a diversity of things. And I was wondering, what is your approach within your group to tackle that issue or that challenge, not issue, but challenge? And do you work with people who have very diverse profiles within the group, or do you tend to collaborate externally? And how is that working? So what is your composition, let's say, of the team in facing that challenge?
I mean, I think it's always super hard because it's not just that you don't have the same expertise and the same vocabulary, but people have different motivations or sometimes just very different requirements. Yeah, kind of silly. I actually do lots of things with the construction industry too, and maybe I should have included more pictures of that, but I didn't. So, and there, you know, sometimes really, I collaborate a lot with James, who I worked on the cardboard machine kit with, who does architectural. He's like the head engineer for Zaner, a architectural metal fabrication company that also they do like all of Frank Gehry's buildings. They always run into these problems where the digital design is super complicated, and how do you actually manufacture something that has 100,000 different parts? And then, I don't know, sometimes I'll go to some architecture schools like Bartlett or whatever, and they're like, oh yeah, manufacturers are all like very risk averse and they never do anything new and everything's crazy. And they don't really take into account that, you know, if a manufacturer delivers parts that result in the building leaking, they just get sued. You know, it's not there's no upside to taking on these risks necessarily. It's not like it's not like the same incentives exist for them as exist for the architects who are making these different designs. And so, yeah, how do you do these different kinds of tasks, and how do you help people collaborate? I think a lot of it has to do with thinking about the incentives for something, and why would you collaborate, and what is going to result in people wanting to actually have the best outcome for the project. So with Eleftheria's lab, for example, the material science lab that we hang out with, her lab is really interested in developing new materials. Their expertise is developing new materials. They don't necessarily build things with those new materials because that's not their expertise. Their expertise is making new materials. But you don't build cool stuff with materials. People outside of material science don't tend to get super excited about dog bone samples. So, so like the collaboration there is more about, okay, what can we do together to explore the possibilities that these new materials enable? And also, you know, for me, a big interest that I have is, how do you make it easier to do this kind of experimentation and iteration? So I'm always looking for collaborations with people who want to push that. I'm not trying to just like make machines for other people. I'm trying to understand at what point is it easy enough for people to make and customize their own machines. And so, you know, I want to work with people who are also incentivized to explore that and are willing, you know, even if you're a material scientist, that you're willing to like open a Jupyter notebook and try to like experiment with your toolpaths. Or even if you're a manufacturer, that you're willing to say, okay, yeah, let's test out like this weird way of measuring how these different panels got placed and comparing them to the CAD model, who are willing to even open CAD in the field and think about how that impacts their job site. So yeah, I don't know. Basically, you got to talk a lot. It's hard. Communication is hard, especially on Zoom.
Indeed. Actually, we have a couple of students who are working on their thesis in these topics, and I see one. Michael is making really big eyes. He's fading out there. I don't know if, Michael, you have a question? No, he doesn't. While you think about a question, I will ask another question. The other thing that I wanted to ask you, Nadya, was, and now I guess in some way, maybe you sort of answered the question that I was going to ask, but you also mentioned, and I thought this was a really interesting parallel, which I personally had never thought about, but the idea of how computational computing went from industrial computing to personal computing in some way, no? And then you were talking about the idea, or in some way the maybe illusion that fabrication would do the same a while ago. And I was going to ask you, how far do you think we are from that, and in what way do you think we will go towards that? But I guess in some way you were kind of hinting at, in the way that you were saying you're not making machines for everyone, but maybe it's a question also of not mass personal fabrication, but rather distributed personal fabrication. So how things can be customized to the needs and uses of different individuals. So creating, I guess, toolkits, which is a little bit what you showed us today as well, where you can plug in different elements. But I don't know if you want to elaborate a little bit more on that. I'd
Totally
about that.
Yeah. I guess the story, I feel like the story that everybody sort of imagines is, oh, we're going to have a replicator in our home, and then like a new cup will come out, and we're just going to print the cup, and then we'll all have the cup. That's like the simplistic story that so many people are just like, yeah, this is the future of digital fabrication. And I guess it kind of assumes that people can't make things now and want to make things in the future. And I think that both of those statements are false. Like, actually, I assume that everyone who's here on Zoom is actually really good at making things. That's how you end up in architecture school. And so there's already this huge expertise spectrum of like making, people who make their own stuff. Like, I make my own furniture. I'm not like super good at it, but then it's exactly right for me. And there's a lot of people who make their own things already. And so it's not coming from zero. It's coming from, okay, well, here are the constraints, here are the materials, here are like the context. This is what we want to do, and this is how we want to build. This is what we want to customize. And then the other thing, which is that, everybody is going to want to do this on their own, is also, I think, a bit, even if you are really excited about making furniture, that doesn't necessarily mean that you're excited about making your own car or your own phone. And so where does the desire to want to customize or build custom things break down? And I think it's much more exciting to look at the domains where people are already doing customization and different kinds of tasks, rather than saying like everybody's grandmother is no longer going to go to the mall and they're just going to like get stuff from their replicators. I just like don't really see how we get from where we are now to that in the future. And so I think that much more likely you have machines and processes that are being developed that are helping people who are already doing some kind of manufacturing or some kind of manual task that they want to automate, or someone who is trying to automate something that's like a data collection process, and that there are many more small tools that are going to be strung together in these sort of bespoke ways, rather than saying like, oh, we're just going to like, everybody's going to have matter compilers. It's just, the world is just going to be like the Diamond Age. It's going to be just like science fiction predicted. I just really don't think so.
Okay, thanks so much, Nadia. I'd like to open the floor. So if anyone has any questions, I don't know if Shahar is the other student who's specifically focusing on this question in his thesis. I don't know if he has a question.
No pressure, students, but you know, who even are you?
They have their cameras on, so I just assumed that they were interested in asking a question.
Can you hear me? Nothing? No.
Now we can hear.
Okay. Hi, Nadia. Very interesting. Thank you for your time and lecture. What I want to ask is, from the project that you've presented to us, you're kind of stating a new role for a designer, which is like the design of the tool. Then the agency goes through, it's not a new role, it's just switching from being architect to being like machine designers or machine engineers. Or, I mean, these roles already exist. So when we do this transfer, I mean, what is the advantage that we have over like an engineer that will have like better prerequisites and better understanding and probably will be better in describing the needs than an architect that improvises code writing or found a wrench in his father's garage, you know? So this is one question. And
yeah, okay.
And then the second question is, on these machines, do you think that in the fabrication process, are we really changing the agency, like the placement of the agency? I mean, does it change from the person to the machine or to the computer? I mean, do we do something that's substantially changing like the essence of the agency, of the design agency?
Sure. Okay. I shall answer both these questions. Well, number one, I think that you know, architects, designers already design machines, or at least they already design workflows and processes. So, you know, the recently open Google HQ, designed by Big and Heatherwick, that I helped a tiny bit on for some of the bash scripting. The architects are very hands-on, trying to understand what is the machine that we can customize or use to be able to achieve our design vision. So it's not like everything is just in your brain and you're like, oh yes, I imagine this like perfect, circus tent like looking structure, and like the manufacturer is just going to take my vision and make it into reality. No, there's like, you're constantly like bringing around, it's just like, this is the sample, like here's the part that I can make, like what is the surface finish, like what are all the ways in which I can customize. So the reality of actually building things has so much to do with manufacturing and the possibilities that are given by the tools that you're using. So even if you're not building a machine from scratch, you're still constantly changing and tweaking and optimizing and heavily involved in this process. And I think that that's really where the magic lies in this communication. And it might be that you can be a designer who doesn't know anything about machines or manufacturing at all, and you just have excellent manufacturing partners that do things with you. But in that case, you have a bigger team than just one person. So you have different people that can play different roles in this workflow, but it doesn't mean that that customization goes away. And in that case, I think that a lot of the design intent is coming from your engineer and not from the designer themselves, because all of these decisions that get made in the manufacturing process end up influencing the final product and the final thing that you end up producing. And so, you know, I guess there it depends on how extensive is your vision actually. Do you just want like a particular shape? You just say, I want this to be 60 centimeters by 40 centimeters, and then you let all of the other decisions be engineering decisions, then yeah, I don't know, maybe then that's all the designer does. I just spec mass housing, and they're all, you know, 60 square meters, 20 square meters, or 40 square, maybe that's all that it is. But I think that there's maybe a lot more that people like to specify. With respect to agency, I think that agency is all with humans. I think that, people sometimes are like, wow, like, oh, we could have these, using deep learning, we can make new kinds of designs that aren't made by humans. But then the design is still made by a human because the human made the model and the model produced the design. It's just a different way of creating the design. So it's not that you specify every line or you don't specify. It's just a different way it's a different way of exercising agency. So it's the same thing if you said, if I made a parametric model and I didn't specify and I didn't bake every single possibility that could come out of my parametric model, that doesn't mean that I don't know everything that my parametric model could do. So yeah, I guess like people who attribute a lot of agency to the technology, I think are just maybe not really seeing where the human decisions were being made. They're like, oh, I can't do anything because this model was given to me or this technology was given to me and I don't know how to change it. But I personally never think I can't change technology. I'm very good at hacking all of it. So yeah, I don't know. I think the agency always lies with the human.
May I take the next one? Perfect.
As far as I'm concerned.
Hi, Nadia. Thank you so much for the lecture. Like full disclosure, I'm not an expert in fabrication, so my question is not going to be so much on the technical sides of your expertise, but because I simply can't. However, I am very intrigued by your natural talent for communication, and I think this is clearly obvious in the way that you present and in the way the passion you kind of like channel when you talk about this topic. I personally I work with data, more the urban realm, and I think we share something in common, which is the digital divide. So accessibility of these, let's say, things that we work on different age groups. Recently, I had the chance to present the work that we're doing at IAAC to a group of 70-year-old architects, and recently I also had the chance to talk with my 10-year-old niece about what we do. So there's definitely a change in narrative, or at least the way you approach the narrative when you talk about these topics to the different age groups. Now, my question is more about how do you actually navigate these changes? How deep do you go into the engineering of the narrative depending on the audience? So for instance, today it's clear, we have more or less an audience of master's students, education, academia. You know that we're going to be very much interested in all the nooks and crannies of what it is you do. But if you speak to different audiences, I imagine that you have to simplify without kind of like dumbing down what it is you do. So that's very tricky,
Yeah, I guess thank you. That's a great compliment. I never really think of myself as great at communicating, but I appreciate your compliment. I kind of think of it in this way. I think it's fine to lose people when you talk about stuff that you do, as long as you start somewhere where everybody can be together and you end somewhere where everyone can be together, and you make it clear when you're at which part. So I care about precision and machines, and then maybe I'll talk a lot about some specific model for being able to identify which plant I want to pick up, blah, blah, blah. And the reason why we care about this is because, just make it clear that, hey, here's going to be like a little technical part and maybe not everyone cares, just don't listen, but we'll be back to your regular scheduled programming. That's, I think, a big part of making clear. So you don't have to, because if you make everything super high level, it's not clear what you're doing. Like nobody understands what the point of it is. So yeah, I think it's okay to like sandwich a bunch of different, you're going to do complicated things with your data that you're collecting in an urban environment. You want to show that that's happening. and how you analyze the data might not be clear to everyone, but maybe someone it's going to be clear to, and that's what they're going to take out of the thing that you're talking about. And then you can say, and the reason that we're collecting all of these data and the reason we're doing this analysis is because we want to be able to design cities in this different way, and our vision is blah blah blah. So yeah, I don't know. That's what I try to do anyway.
Do you think there's space for, let's say, the previous generations to be part of this?
Yeah, totally. I mean, I think I'll go out on a limb and think that there's like not a ton of boomers here on the call, but I think that they have a lot of expertise that's really different from the expertise that you get now as a master's student or as someone who is part of a different generation. And I think it's for different kinds of expertise, it can be really frustrating that you spend all your time learning something or doing something that then is no longer acknowledged or valued or respected. And so, I don't know, just like a respect for that. I was a bachelor's student before Arduino, so Arduino didn't exist yet. And so there were all these things, like there's all these things that I built, you know, when I programmed microcontrollers, I programmed them in assembly, which was really fucking annoying. And then now, you know, like any high school student could do things that I did as a graduate student in like an afternoon. And sometimes most of the time I'm like, that's awesome, everything's great, everything's like, everything's possible, and like we're really making great progress. But sometimes I'm really like, back when I was young, this was harder, and we had to think more about what we were gonna do, and like you just didn't do a bunch of bullshit all the time because it actually took energy. So yeah, you know, like with 70-year-old architects, I imagine that they spent a ton of time making detailed drawings, like all the time, by hand.
Yeah.
And how do you acknowledge that and understand what that means for what we're doing now? You know, like, no, I've never manually made a detailed drawing that someone had to work from, but I have spent a lot of time converting DXF formats. So, you know, there's like overlap, and I don't know, being able to find that shared experience somehow and translate it to each other. I feel like that's important.
Thank you.
Super, thanks, Nadya. Sorry. I don't know if anyone else has any questions. It's now or never.
Yeah.
Okay, fantastic. So I just want to say a huge thank you, Nadya. I think the presentation was super interesting and very, very useful for a lot of our students. Maybe there was just a little bit too much information for the moment, so they need to process.
No, I've been teaching online for forever. It's very stressful to ask questions on Zoom. I totally get it. If any of you guys want to reach out, my email address is nadia@uw.edu. I'm going to be in Barcelona over Christmas, so if any of you have any good restaurant recommendations, you can let me know too. And otherwise, you know, good luck with architecture school. Try to sleep sometimes.
Excellent recommendation. And we'll send you some recommendations for restaurants and things to do later on. Fantastic. Thank you so much, Nadya, again. It was really lovely to have you. And I wish you all the best and safe travels to Barcelona.
Yes. Good luck with the rest of the year, everybody.
Thank you, Nadya.
Thank you.
Bye.
Bye, everyone.
Bye.